Softmax regression, also known as multinomial logistic regression, is an extension of logistic regression that allows us to handle multiple classes. It's particularly useful when we need to classify data into more than two categories. The softmax function, which gives this technique its name, is used to convert raw predictions into probabilities, representing the likelihood of each class. Now let's modify our previous Hello World program to implement softmax regression on the MNIST dataset. Let's understand the modifications we made to our previous code. In the model architecture, we add a final dense layer with 10 units, corresponding to the number of classes in the ANIST dataset. We also set its activation function to softmax. The softmax activation ensures that the output values represent class probabilities, summing up to 1. We changed the loss function to sparse categorical cross-entropy, which is suitable for multi-class classification problems. It internally applies the softmax function and compares the predicted probabilities with the true labels. With these changes, our model is now capable of performing multi-class classification using softmax regression. The model learns to assign high probabilities to the correct class for each input image, allowing us to make predictions based on these probabilities. Now let's summarize what we've covered in this lecture so far. TensorFlow is a powerful open-source library for numerical computation, widely used for machine learning and deep learning tasks. We explored the installation process of TensorFlow, both with and without GPU support using pip. We dived into the world of MNIST, a classic dataset used for handwritten digit recognition, and wrote our Hello World program in TensorFlow. We introduced softmax regression, an extension of logistic regression that handles multi-class classification tasks. By modifying our code, we transformed our Hello World program into a softmax regression model, capable of accurately classifying handwritten digits from 0 to 9. My dear friends, we have only scratched the surface of TensorFlow's capabilities, but fear not. Our journey shall continue, exploring advanced topics such as convolutional neural networks, recurrent neural networks, and more. So brace yourselves for the upcoming lectures, where we shall unravel the secrets of deep learning and empower ourselves with the tools to tackle even the most complex AI challenges. In TensorFlow, computations are represented as directed acyclic graphs, DAGs, known as computation graphs. These graphs consist of nodes, which represent operations or computations, and edges, which represent the flow of data between nodes. But why do we use computation graphs, you ask? Well, my curious comrades, computation graphs bring several benefits. Flexibility. Computation graphs allow us to define complex computational workflows by connecting individual operations in a structured manner. We can perform both forward and backward passes through the graph, enabling efficient computation and automatic differentiation for gradient-based optimization. Efficiency. Computation graphs enable parallel execution of operations, leveraging the full power of modern hardware such as GPUs. TensorFlow's computational engine optimizes the graph and executes operations in the most efficient manner possible. Portability. Computation graphs can be saved and reused, allowing us to deploy trained models in various environments without worrying about the underlying implementation details. Now, let's see how computation graphs come to life in TensorFlow. Take a look at the following example. Let's dissect this code step by step. We import TensorFlow and create a computation graph using TensorFlow operations. Here we define constants a and b using the tf.constant operation. We perform computations on these constants using various operations such as tf.add, tf.multiply, and tf.subtract, creating a complex graph of computations. We define the final node E, which represents the result of subtracting D from C. To execute the computation graph, we create a TensorFlow session using tf session. Within the session, we run the graph using ses.runE, which computes the value of E. Finally, we print the result obtained from executing the graph. As you can see, the computation graph represents the sequence of operations, and TensorFlow takes care of evaluating these operations efficiently, providing us with the desired result. But my inquisitive friends, computation graphs are not limited to simple mathematical operations. They can encompass complex deep learning models with layers, activations, and optimization algorithms, allowing us to build and train state-of-the-art neural networks.